Good day, everyone. We are about to start a keynote session very soon, probably in 1 or 2 minutes. Hi, Prof. Lim.
Hello, hi. Good afternoon,
Hi.
everyone.
Yeah, good day, Prof. Lim. And can you hear me?
Yes, very good. Loud and clear.
Okay, so shall we start right now?
Leave it to you, the chair to decide.
Yeah, for information, I'm the chair for this session.
Oh, okay, cool. Right. So I'll follow your instruction.
Okay, that's great, Prof. Okay, I think before you start your keynote address, maybe I would like to introduce Prof. Lim to all the audience in this room. Okay, for information, Prof. Lim is from Institute for Intelligent System Research and Innovation, Deakin University, Australia. Before we further, I'd like to further introduce Prof. Lim to all. By reading his biodata. Okay, Prof. Lim Chee Peng research focus is on computation intelligence-based system for pattern classification, data analytics, and decision support. He has co-authors, authors over 450 papers, and received 8 Best Paper Awards in international conferences. He has also won several prestigious fellowship for international collaboration, which include the Australia-India Senior Visiting Fellowship, Australia-Japan Emerging Research Leaders Exchange Program, Commonwealth Fellowship, where he paid a visit to University of Cambridge, Fulbright Scholarship, where he paid a visit to University of California, Berkeley, and Visiting Scientist Program of the US Office of Naval Research Global, where he paid a visit to Harvard University and Stanford Universities. So without any delay, over to you, Prof. Lee.
Thank you very much, Prof. Tan. I think I'm very honored today to be here to share some of the research work, and thank you very much to Professor Watada as well, for the invitation as well as the organizing the conference. Since this is a small group, so maybe we'll do this a little bit more informal. So if anyone has anything to ask, okay, please feel free to stop me. We can have some discussion. Just wondering whether you can see my screen. Is that all good? Is that all right? Okay.
Yes.
Okay, so I would start my presentation. Today, what I would like to do is to share some of the works on computational data modeling and focusing on algorithm development as well as some real-world applications. Okay, this is the outline of my presentation this afternoon. First, I'll give a very brief introduction on data analytics and computational intelligence, which is probably a branch of artificial intelligence or AI. And then I'll focus on 3 real-world case studies and to show some of the works that my colleagues and I, including actually Professor Shing Tan and also Dr. Chu Jun Tan, okay, both we all work very closely together, and some of these case studies actually done by them. So I'll go through that later. And let us look at what the evolution of data analytics or goes from 1960s up to the emerging technology of big data today. Back in 1960s, with the introduction of computers, tapes, and all these big disks for data collection, okay, what we can do with all these so-called computers is maybe ask some questions, okay, from the business analytic perspective, like what was my revenues in the last 5 years. So we collect data, then we analyze data. So back then in the 1960s, now we can get the total, average, and etc. from the data that we have collected. Then with the evolution of digital technology in the 1980s, okay, relational databases becomes popular. Oracle, IBM, Microsoft, all these companies now started to offer their products for data analysis, and then with that kind of capability, we'll be able to delve into the questions like what were the unit sales in New England last month. So instead of just a very specific kind of overview like averages, sum, and etc., we can zoom in into a particular location or a particular unit to see the segregation of the data. Then in the 1990s, with the SPSS and Cognos, all these databases now coming online, the OLAPs or online analytic processing becomes popular. And then the questions that we can answer by analyzing our data go into a layer of another analysis, like what were the sales unit in New England last March? Drill down to Boston. So instead of a state, so we can down down to a particular city or a particular, suburbs and etc. And today, the data mining technologies is becoming one of the key enablers for our everyday kind of activities, especially in businesses. So the key question, what we can do with data mining is, what would likely to happen to Boston unit sales next month? So by looking at those questions from 1960 to the current, today's technology, we can see that, instead of just summarizing data, we can drill into a deeper layer of the data analysis. And today, the key thing is to do prediction, meaning that can we use our existing data and then predict it into the future? What would be the trend of those data looks like? So advanced algorithms, particularly in the area of artificial intelligence, becoming one of the key enabler technologies. Right, so these are the basic information of big data. So data analytic, at least in my opinion, okay, involves not just the data analysis part, but also the data processing as well as the storage technology. So to me, data analytics involves three key entities. The first is, of course, analyzing the data. Okay, before that, we need to process the data. After analyzing and also, of course, storing the data. After analyzing, we need to derive insights, from the data. So with these three components, okay, we are saying that we are doing data analytics. And since with the advancements in the digital technology, we can collect digital data, okay, especially digital data in big volumes. So this comes into the so-called big data era. And some of the characteristics of these 6 V's of big data covers volume, variety, velocity, veracity, value, and variability. So we collect large volume of data easily, and then it comes with different types. So it could be text, it could be signals, it could be images, it could be video clips. And then the velocity means the speed of collection is and storage is very fast. Veracity is basically the quality, okay? Because of big data where we collect data from the real world, it could be noisy. There are missing data. So how do we deal with all these problems becomes a very important component. Value. So what will be the value that we can derive from data? I think that is the key thing, whether we can derive, okay, good insights from the data so that decision makers, okay, meaning humans, can make informed decisions based on the data analytic that we perform. So this is the key thing that what we like to show throughout this presentation. And of course, the variability, okay, various ways of formatting and utilizing the data, whether it's through the cloud, whether it's through sharing on nowadays perhaps people are not sharing data on a paper basis, whether it's through a cloud, through email attachment, through databases, and etc. Right, what will be the impact? Okay, this is the business intelligence kind of analysis of big data. According to the statistics published, okay, by in the literature, we can see that, okay, the global business intelligence software market size would probably grow, okay, from 2019 to 2025, okay, from about 25 billions, okay, expected to have a CAGR of 10.1%, which is a very huge market. So the key thing is, instead of doing historical data analysis, we are moving into the so-called predictive analytics. So we are doing data mining, meaning that they will be able to analyze the data, for example, from customers, and then predict into the future what will be the trend of the data, so that we can enable real-time deployment of the data. So that is the key. Okay, instead of analyzing historical data, arriving at a conclusion, we are predicting into the future. This lead us to the so-called from hindsight to foresight. So the first two analytics that we have been doing over the past many years is basically descriptive analytics to answer questions about events that have already occurred, and diagnostics. So to determine the cause of a phenomenon, meaning that we analyze, okay, we collect data, we analyze what are the problems, and so that we can take action. So these are all historical analysis. And moving forward, we are focusing on the so-called predictive and more importantly, the prescriptive analytics. The predictive analytic is basically to estimate the outcome of an event that will happen in the future. An example is, for example, time series prediction of stock market. We would like to know, okay, what will be the index closing index of tomorrow, of the share market, or a week in advance. Okay, that is the predictive analytic. And moving from predictive analytic, we are into the so-called prescriptive analytic. Okay, since we can predict into the future, based on the prediction, what would be the action, okay, to be prescribed for the decision maker, which is humans, to take. So instead of saying that, hey, okay, the stock market trend will go up by, let's say, 5% in the next, 1 or 2 weeks, we'll, produce a list of prescription, just like you go and see a medical doctor. Okay, what do you need to do, okay, in order to take advantage of this prediction? So this is the key of what we are trying to do from data analytics or intelligent data analytics. So we are moving, okay, from information, okay, that is a hindsight, okay, into insight, deriving the insight, and then we try to go into the future of a foresight, and then try to optimize the value that we can derive from data. Right, what would be the technique that is available for us to do so, moving from hindsight to foresight? Okay, one of them is AI. Okay, and this is a definition, okay, which I capture from the web. So AI is basically the science and engineering of making computers behave in ways that, okay, we thought require human intelligence. In the short sentence will be, okay, a machine that is as intelligent as human. So we can say that the machine is an AI. And how about machine learning? Okay, machine learning to me is basically where we can build computer algorithms, especially algorithms that can help us analyze data and then derive insight from the data. And then all these are basically governed by the fundamental laws of human intelligence. So machine learning to me is probably a more restrictive branch of AI, focusing more on computational kind of algorithm from computers, and most probably dealing with data. That uh, lead us to the next definition of CI. So what is computational intelligence? Okay, when we say a computer or a system is computational intelligence, it means that it deals with low-level data, and then it uses pattern recognition technique, to mine information from the database. And then, of course, then it start to exhibit all these so-called AI kind of a property like computational adaptivity, fault tolerance, approaching human-like turnaround, and human performance. So what are the key algorithms or paradigms under CI? Fogel in 1995 defined CI as this technology of neural fuzzy evolutionary systems, which can be used to adapt solutions to new problems and do not rely on explicit human knowledge. It still rely on human knowledge, but not explicitly. So this is the definition of computational intelligence, as well as some of the models under these CI paradigms. So fuzzy computing is basically based on fuzzy logic. Instead of dealing with the Cripps logic like yes and no, right or wrong, fuzzy creates or make use of fuzzy membership to have a degree of belongingness or membership functions. So we can have a membership function of, let's say, 0 0.2 in the hot category and 0 0.8 in the warm category if we have temperature readings of 78-degree Fahrenheit. So instead of saying that, hey, 78 belongs to the warm category, we have a degree of belongingness of 0 0.8 in warm, maybe 0 0.2 in the hot categories. This is basically good at, or fuzzy logic is basically good at dealing with vagueness or uncertainties in human reasoning and decision making. The next main models of CI is ANN, artificial neural network. Basically, ANN models emulate the low-level neuronal information in our brain. So it deals with signals, and what we are trying to do is to model biological neurons. Instead of we have a dendron, axon, and synaptics, then we map it into the input and output. With algorithms to train the output kind of model. And then instead of one neuron, we assemble the neurons in a network structure and then make it as ANN. And then previously, due to computational, especially hardware kind of constraint, we probably restrict artificial neural network to just 2-3 layers, or probably 5 or 10 layers. With the one layer as the input, one layer as the output, and then the rest as the hidden layer. But nowadays, with the advent of GPU and fast computing technologies, we are now moving into the deep learning kind of architecture, where we can probably have tens of thousands of hidden layers in between our input and output layers. But the fundamental principle of deep learning still pretty much hinges on artificial neural networks. And then another big category of CI is evolutionary computing. It started perhaps with the famous genetic algorithm that tried to mimic the reproductions cycles in human, duplicating of chromosome with the crossover mutation, that kind of operation. And then what all this evolutionary algorithm is good at is for stochastic search and optimization. Okay, today, okay, in addition to genetic algorithms, there are tons of new evolutionary algorithm out there. Artificial, what do you call, ant colony technology, particle swarm, and bee and whales, and all these are the new models of computational, evolutionary computational algorithm. Right. Instead of just using one CI models like neural, fuzzy, or evolutionary, the trend now is to form hybrid models like neural fuzzy, neural evolutionary, or agent-based kind of architecture. The rationale is straightforward. Okay, basically we want to take advantage of different paradigms. For example, ANN is good at low-level data processing. Fuzzy is good at high-level human reasoning, and evolutionary algorithm is good at search and optimization. So depending on the problem at hand, so we try to combine them and exploit their advantages, and at the same time try to mitigate their limitations to come up with a suitable hybrid model for addressing the problem at hand. So in my research, I focus mainly on neural fuzzy models, especially the additive resonance theory or ART. So these are some of the examples of models, hybrid models that have been used in my research. For example, FIM-IMIP, fuzzy mimics network. Okay, the key advantages of fuzzy map or fuzzy mimic is they have this so-called online learning capability. Okay, they can learn information, okay, from data, okay, on the fly, from the first data, okay, incoming data to the second to the next, okay, without requiring the so-called batch learning or iterative learning. So that is the key advantage of additive resonance based kind of a model, or generally online learning kind of a model. Okay, as Dr. Tan mentioned earlier, my work mainly focus on decision support. So for humans to accept the predictions from CI models, okay, from basically it's a computer, rule extraction is very important, meaning that instead of just producing a prediction saying that, okay, for example, in a heart attack kind of medical diagnosis situation, instead of saying that, hey, okay, this patient is suffering from heart attack with a probability of 70%. So very obviously, the next question that the user, okay, in this case, perhaps is the medical practitioner would ask is why. So for users, okay, to accept the prediction from a computer or CI models, okay, I believe rule extraction is the key. Okay, nowadays in the literature, we are using the term explainable AI. So to me, this is basically towards opening up the so-called black box of AI into at least a gray box, okay, then hopefully in future into a white box. Right, so these are the architectures of an organization of additive resonance theory. So it's basically is two components. Okay, one is the Art A and one is the Art B. Art A and Art B are unsupervised model. They are linked by the map field. So Art A basically self-organized to cluster input data, whereas Art B self-organized to cluster the target data or the classes. Then the prototypes learned by Art A and Art B are mapped together through the map field, okay, in a way that Art B provide the supervisory signals to the prototypes on Art A. So this is how two unsupervised module of Art are linked together through the map field to form a Art map supervised model. So individually, okay, in the art architecture, there are two main components. The first is the so-called TJ, which is the recognition of the input pattern or vector. So what it does is try to find the closest match between the input data and the prototype store in the top layer or the recognition layer through a function called TJ, which is a fuzzy subsethood between the input and the weight store in the network. And then it adopts a winner-take-all architecture. The highest activated node in the recognition layer is declared as the winner, and then it sends the weight patterns. Okay, that basically is a weight, okay, to the bottom layer again, which and a comparison is made by using the so-called match track vigilance test. So this vigilant test is a very important test, okay, in art architecture to determine the coarseness or fineness of the prototypes to be stored in the network. Okay, for details of art and art map, okay, there are many publications in the literature, particularly from the originator, that is Professors Carpenter and Professor Grossberg from Boston University. Right, so some of the works that over the years my student and I have done is basically to inject probabilistic information, okay, probabilistic properties into the art architecture. So what we did is to come up with a probabilistic version of art where the output can be treated as the online kind of estimation of Bayesian a posterior probability. So this is the demonstration showing that on an online learning basis, how the learned a posterior probability evolves. Okay, when we provide 100 samples to 3,000 samples to the data, you can see that the underlying a posterior probability, okay, becomes more and more accurate when more and more data is provided for the art architecture to learn the underlying distribution and properties of the data. Okay, this is another illustration to show what would be the pattern like when, let's say, 100 samples are given for training, then 1,000, okay, incrementally to 10,000. You can see the evolution of the patterns learned when more and more samples are provided for learning. And instead of just the stationary environment, okay, we can we can also use the art to deal with the so-called concept drift or non-stationary environments. So this is an illustration to show that how art-based model is used to track changes in the data environment. So the right side of the diagram shows that, you know, every 5,000 there is a change in the data distribution, and with a different level of Bayesian optimum rates. And you can see that the art models is able to track changes in the incoming data stream. Right, for dealing with the decision support system, okay, human plays a very important part. So what we have done is, okay, we try to create a so-called human-machine interaction kind of a cycle, so that, okay, instead of for humans to just accept blindly the prediction from the machine, humans can actually provide feedback, okay, into the computers or the CI models, okay, to influence the learning and the focus of the data characteristics that, you know, the machine learning models has formed into its architecture. Okay, I will show some of the examples in the application. So moving on, this is the second part of my talk. Is more on the application. Okay, the first application that I would like to share is the prognosis of discharge conditions of acute stroke patients. So this is a study with real data collected from Asian Stroke Advisory Panel. Okay, the target is classification problem where we try to classify a patient discharged from hospital, okay, with a stroke, whether the after the discharge, the patient would have no symptoms or no significant disability, or with disability, okay, from minor to severe to even to death. So what are the information that we use for this prognosis of discharge condition? Okay, we use the standard information like the age, okay, the sex of the patient, whether it's a smoker, whether it's alcohol consumption, okay, and the history of the patient, as well as the blood pressure, and then other information like cholesterol level and Glasgow Coma Scale kind of information. Going to the in this case is additive resonance theory based kind of a model for prediction. So this is the results that we have. Okay, we can see that when more and more samples, okay, this is basically here the samples patient records are provided. Okay, the learning becomes more and more accurate until it saturates at a level. So this is the demonstration of autonomous learning or online learning. And more importantly, as I explained earlier, okay, rule extraction or knowledge discovery is the key. So instead of saying that, hey, okay, this patient, okay, the discharge condition with the, the predicted discharge condition is with disability with a confidence factor of 0.8. So this confidence factor is derived from the probability as we look at just now, like for example, the risk-weighted Bayesian A posterior probability estimate. So the rules trigger is if the age is high and etc. So high, low, medium, these are fuzzy. So these are the rules that would enable the decision maker, in this case, the medical doctors, to understand better why this particular prediction is provided by the intelligent decision support system that we developed for this particular patient. So rule extraction plays a very important role to allow users to accept the outcome of the decision support systems. Okay, this is a tool. Actually, this tool, is developed by Dr. Chu Jun Tan. Okay, when I was university lecturer at University of Science Malaysia. So, oh, sorry. Okay, it's a video clip that you can see that how this web-based kind of a model is providing decision support for medical doctors. For example, okay, we can enter the patient information when it comes in. The more data we provide, the more accurate the prediction becomes. So this is one of the key data analytic, okay, of dealing with missing data. And then this, as I explained earlier, is the rules trigger. So instead of saying that, hey, okay, this is the predicted outcome, we extract the rules to provide the explanation why, for example, in this particular case, okay, the prediction, okay, is a negative outcome. So the rule extraction parts, okay, provides the justification or the reasoning for the users to understand, okay, what actually is being derived from the computational intelligence models, okay, so that this particular prediction can be considered as a good or bad prediction from the domain expert perspective. So if the domain expert does not agree with the prediction, so this is where the human machine interaction comes in. You can see that, okay, the rules, okay, we project the rules, okay, trigger, okay, from a higher dimension to a 2-dimension, and then you can see that, okay, the medical expert might indicate certain rules in a 2-dimension space, okay, that is far from the extracted rules. Okay, in this case, then we can move around, okay, by using the so-called feedback of good or bad, okay, by the users to rate the extracted rules. And then those rules that are of a lower quality can be removed. and those rules with good quality can be further enhanced. So this is where we are trying to open up the so-called interaction between humans and machines. The second example is actually this example is done by Professor Shing Tan. Okay, is the condition monitoring problem in a power generation plant. So instead of using data from humans like heart attack kind of information, the blood pressure, etc., we collect information from sensors. Okay, temperature sensors, pressure sensor for various points of a particular process called circulating water system in a power generation plant. So what we are trying to do is to provide prediction of the blockage of piping system, okay, of the power generation plant. The power generation plant uses water to cool down the turbine engine. Okay, blockage of the turbine, the circulating water system is a key problem. So we are using various temperature and pressure readings to provide a prediction for the maintenance engineer to understand whether there will be a significant blockage or insignificant blockage in the piping system of the circulating water system. How does it look like? Okay, this is a small video clip showing how this thing is being used in the real world. So the first is basically we collect the data, then let the system do the so-called learning. Okay, the architecture or the model design is additive resonance theory. So this is the rules trigger. Okay, what are the rules that has been learned by the system? So during operation, when the system, okay, when it provides a warning signal, okay, the user can go and see what is the particular rules trigger and what are the readings from various points, so that it can have a better idea of the health condition of the circulating water system. So again, this shows the importance of rule extraction in a decision support kind of setting. How about human interaction? So this is a visualization map of different classes like significant blockage, insignificant blockage, efficient heat transfer efficiency, and good heat transfer process or inefficient heat transfer process of the circulating water system. You can see that the different classes of information. Some are actually overlap between class 1 and 2. And this is where, when the rule is triggered, okay, you will show that whether it's a class 1 kind of a rule or class 2 or class 3 or class 4. So that user can see that, hey, okay, this particular rule is not very accurate because it's sitting in the boundary between class 1 and class 2. So this provides further information for humans to interact with the knowledge capture and learn by the fuzzy ArcMap models. The last application I would like to share is Road Bus. This is a system developed by a company in Malaysia called Neon AI. So what happens is it's trying to use the so-called citizen science or crowdsourcing kind of environment, okay, where users, where citizens can capture information through our smartphone and then report the road condition, okay, to the authority, so that bad condition like pothole on the road and etc. could be detected and rectified as soon as possible. So Road Plus, okay, has all these features like low cost, data driven. Basically, it uses deep learning behind the scene, and it is automated. And the company won the hackathon by the Ministry of Science, Technology and Innovation of Malaysia in 2021. So this is a snapshot of how Road Plus can be utilized. Okay, of course, this video clip shows that deep learning is being used to recognize signboards, okay, on an online or real-time kind of a basis. So by understanding the capability and the real-time accessibility and real-time capability of deep learning models. So how do we utilize all these capabilities in Road Plus? So in digitizing the road and then helping the authority to maintain the road condition. So last but not least, I'd like to show a video clip of this Road Plus. I think in summary, what I would like to share is just a publication from the director of our center, Professor Sai Nahavandi. So instead of, in Industry 5, 4.0 era, we are projecting into the future of so-called Industry 5.0. So what Industry 5.0 would look like is basically a human-centric kind of environment. That's where it leads us to the importance of finding a what do you call symbiosis or integration between human and machines. So this is we are trying to predict into the future and then how to come out with an environment where machines and humans are working together to make sure that we fully utilize the so-called current AI kind of capabilities. With that, I'd like to thank everyone for their attention, and I'll be happy to if there is any questions. Thank you.
Okay, thank you, Prof. Lim, for making a very interesting presentation today. And your presentation is very insightful. May I open question? May I have the question from the floor? Any questions? Okay, I think that Prof. Maybe I start first. Okay,
Sure. Yep.
I have a question. Just now you mentioned that from the beginning of your presentation, you mentioned that the next, I mean, prediction is the next trend in computing, right? So maybe you can suggest how this prediction could be made. Is there any computing model that are available for this purpose?
Yep. I guess in order to fully exploit the capability of data. So instead of just analyzing and understanding historical data, we're trying to predict into the future. There are various type of algorithms, okay, that we can use for prediction in AI, for example, time series prediction, okay, forecasting. So this is a typical and very well established kind of technology or methods that we can use. Okay, basically is from the data perspective that's quite established, saying that instead of doing interpolation, we are trying to do extrapolation. So of course, the challenge of extrapolation or prediction into the future is accuracy. The longer time horizon we predict into the future, the less accurate it becomes. That's for sure. Okay, if we can predict very accurately, okay, probably tomorrow, but a week later, our prediction, okay, the prediction of information a week later from today might not be as accurate. Why? Is because there are various, factors that probably would affect the model and also the data. So these are the key things. So So in a structured environment, prediction could be control. For example, the circulating water system or the changes of the environment factors is low, like for example, medical cases. But in stock market, okay, because of so many factors and the dynamics of the factors, so it becomes very challenging, okay, to predict into the future on a longer time horizon.
I see. Thank you, Prof, for your sharing and
Yeah.
yeah, I noticed Prof Watada raised your hand. Yeah, over to you, Prof Watada. Do you have a question for Prof Lim?
Okay, thank you very much, Professor Lim,
Thank you, Prof. Watada.
for your nice talking, quite interesting. And I have a little bit different question. One question, including several aspects. I'm interested in learning, but I would like to build unsupervised learning. Of course, the human educated and experienced and learn very wide range, but general learning, not the purpose learning, but usually learning in system is to use purpose data and narrow or directed data and learn. You explained such a learning the efficiency 80% or something, but the purpose, for example, driving. But human usually experience in experience and education, general learning. But without learning, we can understand the problem. I can recognize the pattern without the purposed learning. So unsupervised learning has two ways, depending on general learning. Well, without general learning, we can learn each experience step by step, two ways. How do you think about the future direction of deep learning or learning ways in your research?
Thank you, Prof. Watada. Okay, this is a very interesting and of course a very challenging question. Okay, nowadays, okay, instead of using like we see 2 or 3 layer kind of architecture, we have thousands of layer of deep learning kind of architecture. So learning, okay, to me, as far as I understand in the deep learning kind of architecture, is basically focusing on granularity of data. So certain part of the model could probably recognize a bigger picture. That is perhaps I would relate it to the general learning kind of a scenario, like Prof. Watada mentioned. Okay, I look at let's say I look at the picture. I know that this picture is a seaside. Okay, there is a birds, now there is the wave of the sea and etc. And then if I zoom into a smaller portion or a dedicated area of a picture, then I can see that the bird maybe is a seagull and things like that. So that becomes a specific learning to me. So what I'm trying to say is, the learning in our brain, perhaps now we can see that there is a general kind of a learning in terms of a big picture. There is of a coarse granularity, and by zooming into the details, we can do the learn the characteristic of certain things. That is basically a special purpose or very specific kind of a learning. And how do we do that? Okay, I believe deep learning is moving into that direction. So that instead of just purely supervised learning, like Prof. Watada you mentioned, perhaps it's a so-called semi-supervised kind of a learning. I don't believe in a total unsupervised kind of learning at this particular moment. Okay, perhaps in the future. Okay, of course, it will be possible, okay, with more data coming in, but I believe currently semi-supervised is the way to go. Why? Is because of big data. So instead of just probably in the medical diagnosis case, we just have 500 patient records. There are tens of thousands of patient records coming in. So it's kind of hard for humans to tag the outcome one by one. So semi-supervised learning or active learning, coupled with deep learning kind of architecture to focus on different granularity of information, to me is the way forward in terms of database learning systems, including deep learning. I hope I answer your question, Prof.
Thank you very much for nice talking again, Professor Lim. Thank you.
Thank you.
Okay, Prof. Lim, I have a question. Okay, just now you mentioned deep. I mean, by referring to your presentation today, you mentioned a lot of these extracting the rules from neural networks or machine learning model. Okay, but if you refer to the current trend from the scholarly paper publication, it's focused more on deep learning. But we know that deep learning is black box. And in your opinion, how this black box from in the in the deep learning could be open?
I guess that is kind of expected because of thousands and thousands of so-called hidden layer in between. So opening up the black box of deep learning architecture might not be straightforward. But again, with the current development of nowadays, the sexy word for the literature is explainable AI. This is where we are trying to open up the black box of learning systems. So in terms of deep learning, personally, if I were to tackle this problem, I would go back to what I have explained, focusing on the level of granularity of knowledge or information that we are trying to extract from the network or the model. So if we are trying to extract the models rules from a course model, so where would be the layers of information that are we need to focus? If we are going to extract very detailed kind of insight or information from a deep learning architecture, where are the layers of those deep learning models store those information? So instead of just a one-off kind of approach to extract knowledge, personally, I would try to use the so-called divide and conquer, that kind of approach to focus on different level of granularity of information stored in the model. That is
Okay.
my personal opinion. Thank you.
Thank you very much for your opinion, which is very, there is a lot of challenges that we may need to overcome along
Definitely.
this research direction. Huh? Okay, may I invite any other question from the floor?
Yeah, I have one question for Professor Lim. So I'm interested in the prediction because I myself are doing some prediction for the capital asset pricing in the stock markets. And however, I'm usually doing the traditional econometric models. So in econometric models, for example, the typical time series prediction techniques usually we require the time series to be stationary. However, I have seen other like deep learning techniques applied for the stock markets. They never are talking about anything like stationary or checking the stationary. So I'm wondering, does it mean that deep learning has like solved all these kind of stationarity problems? So they never needed to concern about this.
Thank you, Prof. I guess stock market is always a challenge. Especially if you want to have a very good prediction or forecasting into the future. Stationary, I will probably tackle it from the time series kind of perspective, where we probably have different components like seasonal trend and etc. in the data. And then by exploiting those information, we are trying to build a model that can not just handling non-linearity, but also non-stationary kind of information into from the data. So I believe deep learning is not a turnkey kind of a solution at the moment to to tackle a stock market or time series prediction. A lot of research is needed. Currently, I have a student looking into time series prediction, but not, of course, not on stock market, but more on the power consumption. Okay, that kind of more, I would say, less chaotic, less stochastic kind of problem compared with the stock market. So to sum up, I believe we need to focus on analyzing the data into different components, seasonal trend, etc., rather than treat it blindly as a set of data and then try to predict into the future. Okay. The rule of thumb is rubbish in, rubbish out. So we really need to understand our data well before we can extract and go into the details and do good prediction.
Okay, thank you.
Okay, Prof. Lim, I think that we have one more question. I think probably it's the last question for this section.
Sure.
It is from Dr. Prof. Yusuf Ahmad. Yeah, over to you, Prof.
I'm working in a water utility as an IT manager. We started collecting data from 2004 till now about the water consumption, water use, and water resources in our area. You know, Jordan is one of the poorest areas in water resources. So the main purpose for water utilities is to save water and to especially from the resources itself. We start collecting from 2004 the data about the wells we have, the power consumption about these wells, the cost of producing water from the wells and taking it. Till now, we have a vision to supply water for the city, okay, most efficiently. We start replacing our BLCs and the control unit and sensors to be able to not only send data about the situation, about the electricity and power consumption, about the water, about the pressure, about everything, but although it will be active or can react and respond for the action that we want after that. Our vision is to reach fully automation about this supplying water. That means we started building a matrix of data. That means if an area needs water, we can find the lowest cost of wells to produce this water. We start using this matrix and it's working till now very good. Now our vision is to make it more intelligent, more reactive without any human interaction. Some of the data that we are collecting is the population, especially that we are tourism city. So, you know, some days that there is people in holidays, there is more people, there is more traffic, there is more need in water. Hotels works in holidays more. On summer, it is very hot in our places. It's like 40, 50 degrees, sometimes reaches. So you will need more water supply, more. The data for these information already collected from like 15, 16 years now. How to make it, or is it possible these days to make it fully automation using AI or deep mining? Thanks.
Thank you. I think this is a very interesting question and also, of course, a very challenging problem. Okay, I'll probably put that under the smart city kind of initiative. You're trying to provide quality and sustainable water kind of supply, okay, for the city. Okay, I think the key thing is, as you mentioned, you already collected a lot of data over the years. So I believe this perhaps is the starting point where the this so-called deep learning or AI or data analytic kind of a method could be utilized. Okay, one thing which we probably need to keep in mind is, okay, my experience tells me that, okay, as I mentioned earlier, two things. One is rubbish in, rubbish out. Okay, if we do not process the data carefully, okay, and analyzing it, so-called carefully, we probably won't be able to to get any information out. Okay, by using, okay, let's say I have collected the data in an Excel spreadsheet, then I punch it into a deep learning model, and then I would expect it to give very good prediction or outcome or classification or whatever problem that it's trying to solve. Is to me is quite impossible. So in order to have a good outcome, okay, from your data, perhaps you need to understand the data, and then more importantly, pre-process your data. Okay, do data cleansing. I believe there will be quality of data is a big issue. Okay, missing data is something that we need to tackle, as well as perhaps we need to do pre-processing in terms of clustering them into different categories. Okay, before we shun it all these databases, okay, into the so-called AI models. So my suggestion is look into understanding the data and pre-process the data before, okay, throwing all this data into the AI model. Okay, the first thing, okay, we need to do is to make sure that we have a good data to be used with our so-called algorithms. Okay, then you can move to the next. Okay, once you have a good model, then we can move on to the next challenge that you mentioned. Okay, trying to automate it or even predict the usage and all these things. Try to make it into a more automated kind of a process instead of human intensive or human require a lot of human labor efforts. So I believe to just recap, okay, pre-processing, understanding and pre-processing the data is perhaps the first thing to do before you could expect any good outcome from your data analytic models. Thank you.
Okay, thank you.
Okay, okay. I'm sorry that we have no much time for other questions. If nevertheless, if you have other questions, please feel free to write to me. I will forward your question to Prof. Lim.
Sure.
Okay.
Or you can write directly to me.
Yes.
Okay, you can find my email. Yep. And
Okay.
I just want to thank Prof. Watada, Prof. Tan, okay, both Dr. Tan, okay, Chiang, and also Chu Jun, okay, for all the work that you have done as I share in my presentation. Thank you very much to all.
It's not mentioning it, Prof. Okay, and once again, thank you, Prof. Lim, for your interesting presentation. Okay, we hope to meet you again in the next preliminary talk, which will be given by Prof. Chiang. Okay, so right now I announce the section close.
Thank you.
So we'll join in the next keynote section by Prof. Chiang later on. Yeah, thank you.
Okay, so we will start, Professor Peng.
Sure, Prof. Gu.
Okay. Next, let me introduce the keynote speaker 6, Professor Zhang Li. Professor Zhang received her PhD degree from the University of Birmingham, UK, and she is currently a professor in National Subsea Center, Robert Gordon University, UK. She holds expertise in computer vision, deep learning, and evolutionary computation. She is an associate editor for Decision Support System and associate editor for IEEE Access. And also, Dr. Zhang is a senior member of IEEE. So next, let's